Hey guys, my name is e.m.f and I'm still taking you through magnetic fields and electromagnetic induction. I think we stopped on part 20 and today I want us to start from part 21. I think this is part 21. This is electromagnetic induction and magnetic fields. These are past paper questions for physics 9702, paper 4. So part 21, we are starting with the question 62. Remember I said there are about 114 questions. So state what is meant by quantization of charge. You'll see the same question in electric fields. So uh, quantization of charge implies or means that charge exists in specific amounts or charge exists in discrete amounts which are actually multiples of the elementary charge. Remember the elementary charge is taken to be 1.6 times 10 to the power of minus 19 coulombs. So according to Millikan's experiment, charge was found to have values which were multiples of 1.6 times 10 to the power of minus 19 coulombs. So quantization of charge means that charge exists in a discrete and equal quantities. Charge exists in discrete and equal quantities, or you can say charge exists only in multiples of the elementary charge. Which is 1.6 times 10 to the power of minus 19 coulombs. So charge exists in that in multiples of 1.6 times 10 to the power of minus 19 coulombs. That's why we say charge is quantized. Quantization comes from quantity, specific amount, or discrete amount. Charged parallel plates are, as shown in the figure, produce a uniform electric field. Okay. The electric field outside the region between the plates is zero. A uniform magnetic field is applied in the region between the plates so that the beam of protons passes undeviated between the plates. State and explain the direction of the magnetic field between the plates. We answered a similar question earlier on. So, because the particle, which type of particle? The particles are protons, so the protons are positively charged. And in an electric field, the electric force acts in the same direction as the electric field. Electric field is from high potential to low potential, so electric field is downwards, or the electric field is towards the bottom of the page. So when the particle enters the electric field, it means that the electric force is going to be downwards. So the force due to the electric field is downwards. For no deviation, the force due to the magnetic field must be upwards. The force due to the magnetic field must be upwards. And then we now bring Fleming's left-hand rule. The particle is a positively charged particle. By Fleming's left-hand rule, the second finger points in the same direction as that of the particle. So the particle is entering towards the right, or the velocity of the particle is towards the right at entry. And the magnetic force, which is represented by the thumb, is upwards or towards the top of the page. And when you point the thumb towards the top of your page and the second finger towards the right hand side, you'll notice that the first finger will be pointing towards the page. So we say the magnetic field is actually into the plane of the paper. So state and explain the direction of the magnetic field, not the magnetic force, but magnetic field. So we have already said that the force due to the magnetic field must be upwards, since the electric force on the protons is downwards. The force due to the magnetic field is upwards, or must be upwards, since the electric force on the proton is downwards. Okay, so the force due to the electric field, due to the magnetic field must be upwards because the electric force is downwards. I've said the electric force on a positively charged particle is in the same direction as the field, and the field is always from high potential to low potential. Then we can say that by Fleming's left-hand rule, by Fleming's left-hand rule, the magnetic field must be into the plane of the paper, into the plane of the paper. So by Fleming's left-hand rule, the magnetic field must be into the plane of the paper. Okay, so like I said, remember, for no deviation, the electric force downwards must be equal to the magnetic force. And so the magnetic force must be in the opposite direction to the electric force. Also, I mentioned that the electric force is always in the same direction as the electric field. The magnetic flux density between the plates is now increased. So B is now increased. Sketch the path of the protons between the plates. So we know that the magnetic force equals to BQV. So now that they have increased the magnetic flux density, it means the magnetic force has increased. Therefore, it means that the force due to the magnetic field is greater than the force due to the electric field. Therefore, the particle is going to be deviated in the direction of the magnetic force, which is going to be upwards. So they said, sketch the path of the protons between the plates. Now that the magnetic force is greater than the electric force, the particles are going to be deviated towards the top plate. So I'll draw a smooth curve towards the top plate. I no longer need these ones. Now that I know the magnetic force is upwards, and that the magnetic force is now greater, so you draw a smooth curve. Of course, when the particle emerges, it's going to be a straight line because there is no field outside the plates. So you get your ruler and draw a tangent to the curve. So outside, this part here should be straight. That part should be straight because there is no magnetic or electric field outside the plates. So the curve is going to be like that. A stiff straight conductor, a stiff straight copper wire, XY is held fixed in a uniform magnetic field of flux density 2.6 times 10 to the power of -3 teslas, as shown in the figure here. The wire XY has length 4.7 and makes an angle of 34 degrees with the magnetic field. Calculate the force on the wire due to a constant current of 5.4 amperes in the wire. So we need to find the component of either the magnetic field perpendicular to the wire, or we can resolve the length of the wire perpendicular to the magnetic field. So the easiest one would be finding the component of the magnetic field perpendicular to the wire. So I'll draw a line which makes 90 degrees with the wire. So I'm going to draw this line here. It makes 90 degrees with the wire. So I'm going to resolve. I'll be resolving now the magnetic field perpendicular to the wire. So using this angle here, perpendicular to the wire, if I try to take it perpendicular to the wire, this is going to be B sine of 34 degrees. When you resolve the magnetic field B perpendicular to the wire, it is going to be B sine of 34 degrees. Or you could simply say F equals to B sine of theta. So this is the same as B is 2.6 times 10 to the power of minus 3. The current is 5.4. The length of the wire in the magnetic field is 4.7, which is going to be 0.047 meters. Then sine of 34. I'll press my calculator. So you have 2.6 exponent minus 3, then times 5.4, then times 0.047, then times sine of 34. So I'm getting the force as 3.6 times 10 to the power of 3.6 times 10 to the power of 3.69, or 3.7 times 10 to the power of minus 4. Okay. The current in the wire is now changed. So they have changed the current to an alternating current of root mean square 1.7 amperes. So that means the peak current I naught is going to be equal to root of 2 times root mean square, or times I root mean square. So this is going to, of course, the peak can be plus or minus. So this will be plus or minus 1.7 root of 2. That is the peak current. Determine the total variation in the force on the wire due to the alternating current. So the force grows from 0 to maximum in one direction, and also from 0 to maximum on the opposite direction. So maximum force in one direction, or I would say maximum force, or the peak force, maximum force is going to be equal to, of course, I'm using the same formula, B sine of theta. So the maximum force is going to be B is the same, which was 2.6 times 10 to the power of minus 3 teslas. Now the current is now going to be the peak current, which is going to be 1.7 root of 2. The length of the wire has remained the same, which was 0.047. Then the angle has not changed, so that is sine of 34. So this is just the maximum current. So the maximum current is going to be 2.6 exponent minus 3 times 1.7 root of 2 times 0.047 sine of 34. That is the maximum is 1.64. Remember, it is plus or minus. So this is plus or minus 1.64 times 10 to the power of minus 4 newtons. That is the maximum force. It is plus or minus because this is alternating current. It can have a positive I naught and a negative I naught. So the maximum force, the force can be maximum on one direction, and then it can be maximum in the other direction. So since the force varies between positive 1.64 to negative 1.64, it means that the total variation or total difference, total variation is going to be equal to 1.64 minus negative 1.64 times 10 to the power of minus 4. Or you can just multiply it by 2, that is 2 times 1.64 times 10 to the power of minus 4, which is, we just say times 2, which is 3.28. Let me multiply what I have here, 1.64 times 2, 3.28 times 10 to the power of minus 4, that is the total variation. A solenoid is connected in series with a battery and a switch. A Hall probe is placed close to one end of the solenoid as illustrated here. The current in the solenoid is switched on. Now we see that this is a DC and is flowing that direction. The current in the solenoid is switched on. The Hall probe is adjusted in position to give the maximum reading. In other words, the plane of the Hall probe is going to be perpendicular to the magnetic field. The current is then switched off. The current in the solenoid is now switched on again. Several seconds later, it is switched off. The Hall probe is not moved. On the axis of the figure, sketch a graph to show the variation with the time t of the Hall voltage, Vh. So we know that Vh is equal to Bi over Ntq. Before switching on the current and after switching on the current, remember Vh is directly proportional to I. So that means before switching on and after switching off. Before on and after off, the current is 0. That means Vh is going to be 0. Before switching on and after switching off, there is no current, so Vh is going to be 0. I need to increase the thickness here. Okay, that will be enough. So it means I'm going to draw a horizontal line before switching on and after switching off. So before switching on, that is a horizontal line. There is a horizontal line along the x-axis. And after switching off, but then after switching off, the current goes to 0, but I'm going to start from somewhere close to switching off, like that. When we switch on, of course, it takes a very short period of time for the current to reach a maximum value. So the line is not going to be very vertical along the line for current switched on, but it's going to be a very sharp or very steep graph, very steep line. Because when we switch on, now there's a current. Whenever there's a current, there will be a Hall voltage. So when we switch on, then there is a Hall voltage, so the current increases. The Hall voltage rapidly grows to a maximum value when the current becomes maximum. So I'll draw a line like that, very steep. When the current is constant, after it has been switched on, the Hall voltage remains constant. So that will be a horizontal line until the current is switched off. So we shall have a horizontal line here. Then when the current is switched off, the current is going to go to 0 in a very short period of time. So the Hall voltage also goes to 0. Now look at how the graphs are being drawn. On switching on, the graph is steeper, but on the side of current switched on. On switching off, the graph also is going to be steeper, but it's going to be on the side after switching off. That's when the current rapidly goes to zero. It's not going to be a vertical line, but it's going to be a line which is very stiff as soon as the current is switched off. So that is going to be the graph. It's almost vertical, but not very vertical. Okay. So that will be our graph for whole voltage against time. Okay. The whole probe is now replaced by a small coil. The plane of the coil is parallel to the solenoid, to the end of the solenoid. So the plane of the coil is parallel to the end of the solenoid. On the axis of the figure 7.3, which is this one at the bottom, sketch a graph to show the variation with the time of the e.m.f. induced in the coil when the current is now in the solenoid is switched on and then switched off. Of course, we shall just relate to the previous one. We know that the induced e.m.f. is directly proportional to the rate of change of magnetic flux linkage, which is directly proportional to the VH against T graph. So the induced e.m.f. is going to be directly proportional to the gradient of the graph of VH against T. Before switching on the current in the solenoid, there is no current, there is no magnetic field, there is no induced e.m.f. So still, that is going to be a horizontal line along the x-axis before switching on. And also after switching on, there is no induced EMF. I mean, after switching off, there is no induced EMF because the current goes to zero. The magnetic field also rapidly goes to zero. So after switching off, we shall also draw a horizontal line. However, at the point of switching on, you notice that we have a very steep gradient, which is a straight line. A straight line means a constant rate of change or a constant gradient. Therefore, the EMF is going to be constant. At that point, it jumps to a very high value at that point of switching on. And at that point of switching off, it also jumps from a high value to a low value. Of course, after the current has reached a steady value, it becomes constant, where we have a constant whole voltage. The rate of change of flux linkage is zero because the magnetic field is going to be constant. And whenever the magnetic field is constant, the induced EMF is zero, or the gradient is zero. So again, between switching on or between switched on current and switched off current, again the EMF is zero because the current is constant and the whole voltage is constant, so the induced EMF is zero. So again, we have a horizontal line here. However, there are spikes which are in opposite directions because you notice that from the VH against T graph, this gradient is positive, this gradient is negative. So we're going to have spikes at the point of switching on current and switching off current, and the spikes are going to be in the opposite directions. So if the spike at switching on is positive, then the spike at switching off is going to be negative. So you can draw very sharp spikes, very narrow spikes. So this is at switching on, and then at switching off, this should be almost identical. How many box? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have spikes here on switching on and switching off, because this is where there is a change in magnetic field or magnetic flux linkage. So you can also just draw the spikes like this, but I prefer to draw those ones. You can even make them as much narrow as possible, but they should be almost identical. Okay. A Hall probe is placed at distance d from a long straight current carrying wire as illustrated in the figure here. The current, the current, the direct current in the wire is 4.0 amperes. Line XY is normal to the wire. The Hall probe is rotated about the line XY. It is not moved, but it is rotated to the position where the reading VH of the Hall probe is maximum. So it is rotated to a reading where the reading of VH is maximum. That is when the plane of the Hall probe is perpendicular to the magnetic field. The variation, the Hall probe is now moved away from the wire along line XY. So if we move it away from the wire, it is moved away. Remember, the magnetic field is stronger when you are closer to the wire. So when you move away from the wire, the magnetic field decreases. So B decreases because the magnetic field due to a current in a wire are concentric circles whose separation increases as you move away from the wire. An increase in the separation of the field lines implies that the magnetic field weakens as you move further away from the wire. So B decreases. On the axis of figure 5.2, sketch a graph to show the variation of the Hall voltage VH with distance x of the probe from the wire. Numerical values are not required. So VH equals to BI over NTQ. And as B decreases, if NTQ and I are constant, as B decreases, VH is also going to decrease. VH is going to decrease. And for a constant current, the field strength B decreases, or the field becomes weaker as distance from the wire carrying current increases. So since VH is directly proportional to B, then the VH gradient, gradually is going to gradually decrease as distance increases, or as distance from where is D? D is this distance here, 0. What is D? Okay, D is the distance from the wire. So assuming the wire is here, B is here. So as X, distance X of the probe from the wire. So X is the distance from the wire. We are starting from point D and we want to sketch a graph to show the variation of the Hall voltage with distance X of the probe from the wire. Since the wire is being moved away, we are starting from point D. And at point D, VH is maximum. So we are going to start with a certain maximum value here. And as we move away the wire, as we move the Hall probe away, VH decreases because the magnetic field decreases. But this cannot be a straight line. I can't draw a straight line towards, I cannot draw that this is a straight line towards the x-axis. Why? It cannot be a straight line since the field strength does not vary linearly with the distance from the wire. Remember, the magnetic field are concentric circles. The field strength does not vary linearly with the distance from the wire. So, although we are not concerned with the variation between x equals to 0 and x equals to d, since the probe is moved away from x equals to d, I also want you to notice that even though the magnetic field is weakening, the magnetic field does not decrease linearly with the distance, especially when we have concentric circles around the wire. Therefore, this is going to be a smooth curve. This is going to be a smooth curve starting from maximum value and tending towards the x-axis. We may not easily determine the point where where VH becomes 0, or where the magnetic field becomes 0 easily, because the spread is further, but we know that it tends towards 0, or the field weakens. So I'm going to draw a line, this here. I'm going to draw a line which tends towards the x-axis, but not a straight line. A straight line would mean you can easily determine the x-intercept. So that would be the graph. A straight line would mean you can easily determine the distance x from the wire, for which B becomes 0, but we cannot easily determine that. And the magnetic field does not vary perfectly linearly with the distance from the wire. The whole probe is now returned to its original position, a distance d from the wire. At this point, the magnetic flux density due to the current in the wire is proportional to the current. That is, B is directly proportional to the current. For a direct current of 4.0 amperes in the wire, the reading of the whole probe is 3.5 millivolts. Okay, when the DC is 4.0 amperes, the reading of the whole voltage is 3.5 millivolts. The direct current is now replaced by an alternating current of root mean square value, 4.0 amperes. The period of the alternating current is T. Okay, so time for one cycle is T. On the axis of the figure, sketch the variation with the time T of the reading of the whole voltage VH for 2 cycles. So one cycle stops here, the second cycle stops there. Give numerical values of VH where appropriate. Okay, so from calculation, we know that VH equals to BI over NTQ. And they have said that VH is they have said that the magnetic flux density due to the current in the wire is proportional to the current. So VH is going to be proportional to the current, and since the current is alternating, the current is sinusoidal, VH is also going to be sinusoidal, is also going to be alternating. But we can first find the peak current. I naught equals to root of 2 times I root mean square. So the peak is going to be root of 2 times root mean square was 4.0. So 4.0. So it means this is going to be plus or minus 4 root of 2. That is the peak. So the peak current is going to be that. But remember, they said for DC, we had that direct current of 4.0 amperes corresponds to a whole voltage reading of 3.5 millivolts. How about a peak current of 4 root of 2? So if 4.0 is equal to a constant times 3.5, then also 4 root of 2 is going to be equal to the same constant times the value which we are going to call V naught. So when I divide the two equations, I'm trying to find the peak voltage. You can use any mathematical ways. So the peak voltage V naught is going to be, when you divide, 4 cancels. Okay, K times V naught over K times 3.5 is equal to 4 root of 2 divided by 4.0. So V naught equals to root of 2 times 3.5. And when you press your calculator, 3.5 root of 2 that is 4.95. Of course, this is also going to be plus or minus 4.95. So the peak voltage is going to be 4.95. Let me look for 4.95. The scale here is 0.4. So if this is 4.4.8.92, no, 4.95 must be, if this is 4.4, 4.8, 4.92 must, 95 must be somewhere here in the middle of this box. So 4.95 should be here. So my sketch will not go beyond this. Okay, so this is negative 4.95, it is somewhere there. Then positive 4.95. So the graph is going to be sinusoidal. When they said V naught is directly proportional to B. So assuming if there is no current, if at t equals to 0, the current is 0 because this is alternating. If at t equals to 0, the current is 0, then the voltage is also going to be 0. So the graph starts from here. And since one cycle is here, because they said the period is t, so it means I have to divide this into, I look for half. 1, 2, 3, 4, 5, that is quarter. 1, 2, 3, 4, 5, that is half. 1, 2, 3, 4, 5, that is 3/4. So it will reach maximum at 3/4, at a quarter, and go back to 0 at half. It will again reach maximum at 3/4, and then 0 back to 0 at now 1 period. 1, 2, 3, 4, 5. It reaches maximum again for the second cycle to start. 1, 2, 3, 4, 5. Then it goes to 0. Then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then it goes to maximum and again back to 0. So the graph looks like that. You can draw a better graph. What is very important is that the peak values of voltage should not go beyond 4.95 approximately there. You may not easily find 4.95. Let me see how many squares are those. 4.95 minus 4 divided by 0.4. So on 4 I add almost 2.5 squares. It is just very close to 2.9. That's why I say it is almost in this box here. You cannot easily estimate the center, but it's almost in that box. Okay, so that is the graph. You can draw a better one using a pencil. But that's going to be the graph. And lastly, a student suggests that the hole probe in A is replaced with a small coil connected in series with a millivoltmeter. The constant current in the wire is 4.0 amperes. In order to obtain data to plot a graph showing the variation with distance x of the magnetic flux density B, the student suggests that readings of the millivoltmeter are taken when the coil is held in position at different values of x. Comment on the suggestion. Of course, if the coil is held in position at different values of x, the reading will be the student should now switch off the current and immediately take the millivoltmeter reading if the student wants to find reading. Or at each position, the student should rapidly move the coil from the field and take the millivoltmeter reading. Otherwise, If the student doesn't do that, there will be no reading if the coil is held in position for the rest of the time. So comment on the suggestion. So we shall say that an EMF is only induced in a coil when the magnetic flux stroke field is changing or when there is cutting of the field. Holding at each position as the student suggested, holding at each position means that the magnetic field does not vary. The magnetic field does not vary, so no EMF is induced in the coil. Thus no reading. There's no reading on the millivoltmeter. So if you hold the coil in one position, there will be no change in magnetic field, therefore there will be no induced EMF, giving no reading. Alternatively, you could say at each position the student should switch off the current and immediately take the millivoltmeter reading if the student wants to take the readings. So you'd say at each position, the student should switch off the current and immediately take switch off the current and immediately take the millivoltmeter reading. Because since we have a DC, switching off the current means the current changes from a constant value to zero. In the process of changing from a constant value to zero, the magnetic field also changes from some value to zero. In that process of changing, there is a reading of the millivoltmeter which lasts for a very short period of time. Or at each position where the student is holding the coil, let the student rotate or rapidly remove the coil from the field. Or at each position, The student should rapidly withdraw or remove the coil from the field and take the millivoltmeter reading. So instead of holding just at each position, take the coil at the position, then rapidly move it away. In the process of rapidly moving, there is a change in magnetic field which causes an induced EMF. Okay, so that is part 21. See you in part 22. Until next time, bye bye.